Hi, and welcome back to our flipped classroom. And today we're continuing our conversation on gas laws. So we have already learned three laws within our gas laws unit. We have learned Boyle's law that tells us that pressure is inversely proportional to volume when we're at constant temperature. So that means that as pressure increases, volume decreases, or as volume increases, pressure decreases. And we express that as P1 V1 equals P2 V2. And then we learned Charles' law. And Charles' law told us that volume is directly proportional to temperature if pressure is constant. And we express that as V1 over T1 equals V2 over T2, provided that temperature is in Kelvin. And then the third one that we've learned is Gay-Lussac's law, which says that pressure and temperature are directly related, provided that we have a constant volume. And so we express that as P1 over T1 equals P2 over T2. And temperature, again, has to be in Kelvin. So today we're going to learn three more laws, and those are very simply, the first one is called the combined gas law. So the combined gas law does exactly what it sounds like. It combines the three laws that we've already learned, Boyle's law, Charles' law, and Gay-Lussac's law, into one law that relates pressure, volume, and temperature. And now the only thing we're holding constant is the amount of gas, the number of molecules or the number of moles. And so our combined gas law is P1 V1 over T1 equals P2 V2 over T2. So now, again, temperature has to be in Kelvin. Pressure and volume can be in any units, but they have to be the same units. So we can change two of our variables and see what the impact is on the third variable. So that's our combined gas law, pretty simple. The next one is called Avogadro's law. And Avogadro's law tells us that the volume of a gas is directly proportional to the number of moles. And this just makes sense, right? When we put more air in a balloon, the balloon gets bigger. And so volume is directly proportional to number of moles, providing that temperature and pressure remain constant. And then the third law that we're going to learn is called Dalton's law of partial pressures. And Dalton's law of partial pressures says that for a mixture of gases in a container, the total pressure is equal to the partial pressure, the sum of the partial pressures of each of the gases in the container. So this is most often used in a practical sense in the chemistry classroom when we talk about the pressure of gases that we collect over water, because there's always going to be, when we collect gases over water, there's always going to be some water vapor in there. And so if we want to know the total pressure of that gas, then we have to subtract out the pressure of the water. And this follows logically Dalton's law of partial pressures from kinetic molecular theory. Remember, the gas molecules of each gas are not interacting with one another. They don't exert any forces on one another. And the collisions that they have with the walls of the container are independent of the collisions of the other molecules with the walls of the container. So the total pressure is the sum of all of those collisions. It's the sum of the pressure exerted by each gas. So let's take a look at solving some problems like this. Okay, so this is the worksheet that you have today, and the first one we're going to do together. So here we have the combined gas law, and it says if I initially have, and this again, like the first one that we worked on, tells you which law you're going to be using. So this one says to use the combined gas law. It says I initially have a gas at a pressure of 12 atmospheres, a volume of 23 liters, and a temperature of 200 Kelvin. So just like all of our other gas laws, we're going to go ahead and write down the variables that we know. So we know that P1 is 12 atmospheres. We know that V1 is 23 liters. And we know that T1 is 200 Kelvin. It says, then I raise the pressure to 14 atmospheres. So I know that P2 is 14 atmospheres. And I raise the temperature to 300 Kelvin. So now T2 is 300 Kelvin. And it says, what is the new volume of the gas? So volume 2 is the thing I'm trying to find. So my equation is the combined gas law, P1 V1 over T1 equals P2 V2 over T2. And so I'm going to plug in my values. I have 12 atmospheres times 23 liters divided by 200 Kelvin equals 14 atmospheres times some volume divided by 300 Kelvin. So in order to solve this problem, I'm going to divide 14 by 300, and I'm going to multiply 12 times 23 and divide by 200. So 12 times 23 divided by 200 is 1.38, and that's atmospheres times liters over Kelvin equals 0.0467 times V2, oops, and this is atmospheres per Kelvin. And so now to get the V2 by itself, I'm going to divide both sides by 0.0467. And we are going to get that our new volume is 30 liters. And because 200 Kelvin and 300 Kelvin each only have one significant figure, my answer is only going to have one significant figure. So that's how we do a combined gas law problem. And now you guys are going to work out these two on your own, but we're going to practice an Avogadro's law problem. So we are actually going to tackle number 5 together because it has a little bit of a trick to it. So this one says that we have, remember Avogadro's law is V1 over N1 equals V2 over N2. And so we have 0.76 moles of gas. So that's N1 equals 0.76 moles. And the volume is 17 liters. So V1 equals 17 liters. It says if an additional 0.24 moles of gas are added. So we have to pay attention because it says additional are added, right? And so our N2 is not 0.24 moles of gas. It's 0.24 more than this. So we have N2 is 0.76 plus 0.24, which is 1.00. And our V2 is what we're being asked to find. And so we have 17 liters, that's our V1, over 0.76 moles, that's our N1, equals V2, that's the thing we're trying to find, over N2, which is 1.00 moles. And so in order to solve this, I'm going to multiply both sides by 1 mole, and my units are going to be liters. And we have 17 divided by 0.76 times 1 gives me 22.4. But because I only have 2 significant figures, we're going to say that V2 equals 22 liters. And that's how we solve an Avogadro's law problem. This one, the first one that you guys are going to do, does not require you to add. So I thought we'd take the challenging one together. And number 6, you want to pay attention because it tells you how many moles of gas it has initially, and it tells you that some moles of gas leave. So you're going to have to do some subtraction to figure out how many moles are left. And then Dalton's law of partial pressures. So this is our final law. So remember, Dalton's law of partial pressures is that the total pressure is equal to the sum of the pressures. So pressure 1 plus pressure 2 plus, and on for as many gases as we have present. So number 7 says a sample of nitrogen gas is collected over water at a temperature of 21 degrees Celsius. And the equilibrium vapor pressure of water at that temperature is 19 millimeters of mercury. And it says, what is the pressure of the nitrogen gas if atmospheric pressure is 765 millimeters of mercury? So we know that the total pressure here is going to equal the partial pressure from the water plus the partial pressure from the nitrogen. And those are the only 2 gases we have. And we're told what the total pressure is, the atmospheric pressure. So we're going to put 765 millimeters of mercury here. The pressure from the water, it tells me, is 19 millimeters of mercury. And the pressure from the nitrogen is what I'm trying to find. And so I'm going to subtract 19 from 765 to get the pressure of the nitrogen. And that tells me that the pressure of the nitrogen is 746 millimeters of mercury. And that's how we solve Dalton's law questions. So, as always, I look forward to seeing you and hearing your questions, and I'll talk to you soon.